everyone, welcome back to the IGCSE Physics Possible Walkthrough series brought to you by ZNotes. I'm Yumna, but I'll be your host. We have an amazing contributor, Rushul, who will be guiding you through all the key concepts and questions for this past paper today. Together, we'll make sure you're well prepared and confident for your exams. Don't forget to hit subscribe so you don't miss any episodes. Let's get started and dive into this paper.
Okay, so this is the winter 2023 paper 4-2, which is theory. So yeah, let's begin. So the first question says a car accelerates uniformly in a straight line from rest at time t equal to 0. At t equal to 3.2 seconds, the speed of the car is 13 meter per second. Calculate the acceleration of the car. So as we know, acceleration is equal to the change in velocity by change in time. So here that is 13 meter per second since it's from rest by 3.2 seconds. So that is 4.1 meter per second square. Explain in words what is meant by the term acceleration. So we know that acceleration is like generally the increase in speed, but we can just say it as the change in speed. So it's the change in speed over a period of time. So we can just describe it as the rate of change of speed. The word rate means like change of speed per unit time. The car travels at 13 meter per second from t equal to 3.2 to t equal to 12 seconds. So what this line tells us is that the car travels at one fixed constant speed in that time period. Now it asks us to plot the speed time graph for the car from t equal to 0 to t equal to 12 seconds. So we know that at 3.2, which will be around, so this point would be 2.4, 2.8. So this would be 3.2 seconds. So up until this point, its speed is going to reach 13 meter per second, which is approximately here. So we have to draw a straight line from the origin to this point, and it has to be a straight line because it mentions that the car accelerates uniformly, so it has to be a straight line. And then as we noticed, it says that the car now travels at 30 meter per second till t equal to 12 seconds. So until here, which is t equal to 12 seconds, we just have to draw a horizontal line because the speed was constant. So yeah, this is approximately how the graph should look like. Part 2 asks us to determine the distance traveled by the car between t equal to 0 and t equal to 3.2 seconds. So we know that distance is equal to speed into time. So speed into time, when you look at this graph, is, speed into time is the area under the graph. So we can also take distance as uh, the area under the graph. So the distance here, the area under the graph will be a triangle because we're looking at this area only till 3.2 seconds. So this is the area we're looking at. So this is the area of the triangle. So it's going to be half into base into height, which is going to be half into here. The base is 3.2 and the height is 13. So the answer of this one should be 20.8 or just 21 meters. The car decelerates from 13 meter per second to 0 meter per second at a constant deceleration. The mass of the car is 1350 kgs and the car travels 13 meters in 2 seconds as it decelerates. Show that the work done by the car as it decelerates is approximately 1.1 into 10 to the power 5 joules. Okay, so we know that work done is equal to force into displacement. So we also know that force is equal to mass into acceleration. So mass of the car is given as 1350 kg into the acceleration is one thing. We'll have to figure out ourselves. So it accelerates from 13 to 0 within 2 seconds. So its acceleration is 13 minus 0 by 2. Since we're finding out the change in velocity, the initial or final, the order really doesn't matter too much in this case. So when we do this, the force is 8775 newtons into a distance of 13 meters, which is given. Hence, the total work done is 114,075 joules, or 1.1 into 10 to the power 5 joules. Hence, we have shown that the work done is this much. So, part D says that another day the car in part C travels a longer distance while it decelerates from 13 meter per second to 0 meter per second. The deceleration is constant. Suggest and explain what causes the stopping distance to increase. So, we know that the work done will be constant because work done is also a change in energy, and the change in kinetic energy, because the initial kinetic energy of the car is the same, it will be the same. So, if the stopping distance increases, that means the force would have to decrease to keep the work done constant. So if you draw like a tiny visualization, so basically the car applies a force backwards to basically put the brakes. So that's how like the car decelerates, because the net force is backwards to where it's moving. So now if you want this force to decrease, so presently the car is moving towards the right. It just applies a force towards the left for the force, for the speed to decelerate, and so that the car stops. So now we have to assume that while the car is moving rightwards, this leftward brake force, the total brake force, is not just the brake force by the car. We have to assume that there's also some air resistance that is to be taken into account. So that some air resistance is also opposing the motion of the car, which increases the like backward force on the car. So while the car's braking force might be constant, to decrease this value of force, it might be possible that this the air resistance, the resistive forces might decrease, which would lead to a greater braking distance. So the suggestion is that we can write air resistance is lesser, so air resistance decreases. That means the explanation is that smaller there's a smaller net force. Hence, because of the smaller net force, uh, it takes longer to brake, so the braking distance increases. Yeah. So yeah, that's our explanation. Question 2 shows a tumble dryer used to dry wet clothes. Hot air blows into the drum. The air gains water vapor from the clothes and then leaves the drum. The moist air enters the condenser. Cool air leaves the condenser, passes through the heating element, and enters the drum again. State the process by which the hot air removes water from the wet clothes. So what's happening here is the hot air comes into contact with the wet clothes. It transfers its energy to the water in the wet clothes. So they gain energy, which so more of the particles gain kinetic energy, which allows them to break free from the water and evaporate. So here, what's happening is evaporation. Next, it says that the air is cooled as it passes through the condenser. Describe and explain one other way in which the air leaving the condenser is different from the air entering the condenser. So what happens is, so the air entering the condenser is coming from the washing machine, and it contains all of the water vapor that comes from this evaporation mentioned in the previous step. So it has lots of water vapor as it enters the condenser. As it enters the condenser, the condenser cools this air. So as it's cooling the air, the water vapor also cools in this air and converts into water, as shown here. So as it converts into water, there's a much drier air that exits the condenser. So we can just write that the air that exits the condenser is drier than the air that entered it. The explanation is that the water in it condenses as the air is cooled down and remains back in the condenser. Part B says that the drum of the tumble dryer rotates, lifting up the wet clothes, which then fall down through the hot air. Name the force that causes the clothes to fall down. This is a very basic question. We just know that gravity is what causes the clothes to fall down. When the part 2 asks us that when the drum rotates too fast, the clothes remain in contact with the wall of the drum. State the direction of the resultant force on the clothes during the circular motion. So we know that as the clothes must be moving in the drum in a circular motion, the force is always perpendicular to the line of movement towards the center of the circle. So you can decide that the direction of resultant force on the clothes is perpendicular to their motion. Part C says, suggest why using a clothesline to dry clothes in the open air is better for the environment than using an electric tumble dryer. So this is basically using the fact that a clothesline would use either wind energy or solar energy, which are both renewable sources of energy compared to perhaps the fossil fuels that would be used to produce the electricity which is being used by the tumble dryer. Part C shows a balloon of mass 15 grams which is glued to a straw, which is then threaded onto a horizontal string. The balloon is filled with air and then the air is released. As the air leaves the balloon experiences a force. The balloon accelerates from rest until it reaches a constant speed. It then travels 0.67 meters in 0.18 seconds at this constant speed. Explain in words what is meant by the term impulse. We know that impulse is either the change in momentum or the force multiplied by the time that it acts on the body for. Calculate the resultant impulse on the balloon while it is accelerating. So as I mentioned, impulse is also equal to the change in momentum or mass into the change in velocity, since that's momentum. So we know that the change in velocity is the so we know that the velocity is distance by time. So the distance traveled is given, so is the time. So 0.67 by 0.18. So the velocity we have is 3.72. And the mass is also given as 0.015 kgs. So the impulse should be the change in momentum, which is this mass into this velocity, which is 0.056 Newton seconds. Part 3 says, explain how momentum is conserved as the balloon accelerates. So as the balloon accelerates, it exerts a force on the air which escapes. So the balloon's momentum is this side, but then there's air which is escaping the balloon as it moves forward. We can see the air is released, is mentioned. So the air moves this side. So you know that velocity and momentum are both vector quantities, so direction matters. So while initially the momentum was zero because the balloon and the air was stationary, now one has a momentum this side. Let's take it as a plus, and the other is in the opposite direction. So it'll have a negative momentum, which is minus. So we can say that the air moves in the opposite direction. Its momentum is equal to the momentum of the balloon. So since the momentum of the air should be about minus, let's say minus a, and the momentum of the balloon would be plus a. So when we have a plus a minus a, the total momentum is zero. Thus momentum is conserved. We should write it's equal and opposite to the momentum of the balloon. So thus total momentum is conserved. Figure 3.2 shows the directions of two forces acting on a different balloon as it moves. Determine the magnitude and direction of the resultant force on the balloon. So for this, we have to draw a simple vector diagram. So we know we'll take a suitable scale. So for example, 0.4 newtons, we'll take that as 4 centimeters, since 1 centimeter per zero point 0.1 newton. So we draw a line 4 centimeters like this. I can't measure the distance here, but you can on your exam. So we draw a line of 4 centimeters like this. Then we draw a line downwards of 7.4 centimeters. Then from the starting point, we join the ending point of this line. So this is our resultant force vector. So direction would be this angle relative to the horizontal force, which would be a line like this. So this angle, when we measure it using a protractor or trigonometry, is going to be the direction, and the magnitude will be this this line. You measure it and then you multiply it by 0.1. So just by Pythagoras theorem, I can figure out it's about 0.81. Sorry, 0.84 newtons, whereas this line is 8.4 centimeters. And the direction will be whatever angle you measure of this angle. Next, figure 4.1 shows a bottle part filled with water. The air inside the bottle is at the same pressure as the air outside the bottle. The bottle and its contents are at a room temperature. The temperature of the bottle and its contents are increased. Explain in terms of particles how the air pressure inside the bottle changes as the temperature increases. So you know that as the temperature increases, the kinetic energy of the particles increases. Since they absorb the heat energy, they get more kinetic energy. Kinetic energy of the particles is directly proportional to temperature of the particles. So as the kinetic energy increases, their speed increases, so they move faster. Hence, they collide with the walls of the bottle more often or more frequently. Hence, there's a greater change in momentum per second, or there's a greater force exerted on the walls of the bottle. There's a greater pressure. The lid is removed from the bottle. State and explain how the air pressure inside the bottle changes. So we know that all these particles in diffusion, they move from an area of high concentration to an area of low concentration. And the same kind of principle works with pressure difference. So we know that inside the bottle right now, the air pressure is really high because of the high temperature, and outside it's lower. So as we open the bottle, the pressure reduces, since the air particles which are in at a high pressure inside the bottle, they escape and go out into the room until the pressure of the room and the bottle are balanced. So you write it as pressure decreases of the bottle, explaining that air particles escape until the pressure of the bottle and of the room is equal. The mass of the water in the bottle is 0.18 kgs. The specific heat capacity of water is 4200 joules per kg per Celsius. Calculate the thermal energy needed to increase the temperature of the water by 20 degrees Celsius. Now, we know the formula that energy is equal to mass into specific heat capacity into change in temperature. So nothing complicated. We just have to plug in the values, which are 0.8 into 0.8 into 4200 into 20, which is about 15,000 or 15 kilojoules. Now, another plastic bottle is filled to the top with water. The height of the bottle is 40 centimeters. The density of the water is 1 into 10 to the power 3 kg per meter cube. Calculate the pressure difference between the top and the bottom of the water. So you know that pressure in liquids is H rho G, which is depth into density into acceleration due to gravity. Now, density of the water is the same, acceleration due to gravity is the same. What changes? The depth. So when we have to calculate pressure difference, it'll be the difference in height into the density into acceleration due to gravity, which here, since the difference between the bottom and the top of the bottle is 40 centimeters, the height difference would be 0.4 into density of 10 to the power 3 into 9.8, which is 3900 Pascal. To be more specific, it's 3920 Pascal, but two significant figures is enough. Question 5 shows a road junction, a moving car, and a stationary truck. The road has high walls on each side. The driver of the truck is at position X. The car moves around the corner. On figure 5.1, label a point Y on the road where the truck driver first sees the car. So we know that the line of sight of the driver cannot cross through these lines because the walls are very high. So if we were to mark the first point, we have to mark it going exactly very close to this edge, almost touching it. So if we can draw a straight line like that, it should end up around here. So this would be the point Y where the truck first sees the car, or the truck driver to be specific. A plane mirror is placed at the road junction as shown in figure 5.2. Show how this mirror allows the driver of the truck to see the car when it is at the position shown in figure 5.2. Now, this mirror, so what's basically happening is this is the car. So any light rays bouncing off the car may end up hitting the mirror. The angle has to be proper. Maybe hitting the mirror at an angle such as this. Yeah, such as this. So we know that this is a plane mirror, so reflection will happen. So according to law of reflection, this is the normal. So angle of incidence should be equal to the angle of reflection. So at around a similar angle, the light will be reflected off this mirror, and thus the light will reach point X. So this is how this mirror will allow uh, the truck driver to see the car from even this position when there's walls here. The truck driver wears spectacles to correct long-sightedness. The figure shows how a blurred image forms on the retina. Any effect of the cornea on the rays of light can be ignored. Show how long-sightedness is corrected by adding a suitable lens and continuing the path of the three rays until they meet to form an image. So what happens in long-sightedness is that you can't focus on short distanced objects very precisely because their light is very diverging, and you can't really refract it enough to form an image exactly on the retina. As we can see here, the image will form somewhere behind the retina. So basically we need to use a converging lens. All we have to do is basically reduce the focal length and make the rays converge a bit so that they can be perfectly converged by the lens. So the converging lens or the artificial lens basically does some of the job of the real lens when the real lens is incapable of doing so, such as in this situation. So this is what long sightedness is. So what we have to do here, we have to draw a converging lens, and then we have to show how these three light rays basically are refracted by the lens. So let's yeah. So and after that, what we have to do is we have to show that all the natural lens, that is, also further converts these sorry or converges these rays of light to perfectly form an image on the retina. So there's 4 marks for this. So let's get started. We need to draw a converging lens here. What will happen is these rays enter this lens. Now they will get refracted and fall kind of parallel and straight on the natural lens, and from here they'll get refracted just about enough to uh, meet exactly at the retina. So this is a very rough diagram, but I'm sitting on a laptop. I'm sure during the exam with a proper scale and pencil, you guys will be able to do this. So yeah, this is how the lens helps to focus these images. It would be better if I could make the refraction more obvious and sharp. Yeah. Figure 6.1 shows the circuit diagram for a flashlight, which is a torch. The current EMF of the battery is 4.5 volts. The circuit contains a fixed 60 ohm resistor. The current in the diode is 0.02 ampere. So since this is a series circuit, that means the current is constant everywhere. So the current in this circuit is 0.02 ampere. Calculate the potential difference across the LED. Now, before calculating the potential difference across the LED, we know that since this circuit is in series, the potential difference of the battery will be divided between the LED and the resistor based on a ratio of the resistances. So we know the resistance of the resistor. So it's easier to first calculate the potential difference of the resistor, then subtract that from the total to find the potential difference of this lamp. So we know the formula V is equal to IR. So the potential difference of the resistor is equal to 0.02 ampere into 60 ohms, which is 1.2 volts. So since the total EMF of the battery is 4.5, that must mean that the potential difference of the lamp is 3.3 volts, which is 4.5 minus 1.2. Explain why the LED does not light up if the battery is reversed. So we know that at the end of the day, the LED is just a diode which prevents current flowing through the other direction. It basically allows current to follow one specific direction. The chemical energy stored in the battery is 1050 joules. Show that the flashlight operates for approximately 3 hours. So we know the formula that energy is equal to IVT. So hence here, since we have to show that we need to show a time, we can rearrange this formula saying that time is equal to energy by current into voltage, which is 1050 joules by 0.02 ampere into voltage of 4.5 volts. This would be 11,700 seconds. So now this is in seconds because SI units. So we have to convert this into hours. So 1 hour has 60 into 60 seconds, which is 3600. So if we divide this by 3600, we get 3.24 hours, which is approximately 3 hours. We get this right, which is approximately equal to 3 hours. Calculate the total charge that flows through the LED in 3600 seconds. So you know that current is just the rate of flow of charge, which is charge by time. So charge is equal to current into time. So current into time will be 0.02 ampere into 3600 seconds, which is 72 coulomb. There. Now, question 7. The figure shows some uses of electromagnetic radiation and different regions of the electromagnetic spectrum. Draw a line from each use to the correct region of the spectrum. One of them has been done for you. So, you know that thermal imaging uses infrared because infrared rays are used to to basically hot objects emit infrared radiation, as we see on those images where it's either blue, green, red, or yellow, which shows the amount of heat energy. So that's why thermal imaging uses infrared rays. Photography of people's faces, which is normal, the photos we click, we just use light that is visible to all of us, which is visible light. Sterilizing medical equipment is, of course, done by gamma rays because, well, first off, it's the only option left. Secondly, it basically gamma rays are so highly ionizing and damaging they can kill any like microbes. That's why they used to sterilize medical equipment. and they can go through the like sealed packaging. So once the equipment is packed and sealed, it can be sterilized without having to opening it up and risk contamination. Draw a line, sorry, state the speed of the electromagnetic waves in a vacuum. So we know that this is a fixed value, the speed of electromagnetic waves in air or in a vacuum, though it's slightly lesser in air, but negligible difference, is 3 into 10 to the power 8 meter per second. A Bluetooth headset can be used to listen to music on a mobile phone without the need for wires to connect the headphone to the phone. The headset uses frequencies in the range 2.4 to 2.48 gigahertz. Calculate the wavelength of the radio waves when the frequency is in the middle of the frequency range. We know that the speed of a wave is equal to the wavelength into the frequency. So by rearranging the formula, we have that wavelength is equal to velocity by frequency. So the frequency in the middle of the range will be, 2.4 plus 2.48 by 2, which we simply know as 2.44 gigahertz, not megahertz, gigahertz. So the wavelength would be the velocity, as we know, is 3 into 10 to the power 8 by 2.44 into 10 to the power 6 because gigahertz. Sorry, 10 to the power 9 because gigahertz. So this would be 0.12 meters. So that's why a Bluetooth headset only works well over short distances. This is because the signal can't really pass through walls, and it weakens over long distances. Thus, a Bluetooth headset works well. You'll notice that if you have a Bluetooth headset connected to something and you move even out of the room slightly far, it gets disconnected. This is why, because its signal really can't pass through walls, nor can it travel a long distance in the air. The isotope uranium 235 is represented by the symbol below. State what the numbers 92 and 235 represent in the symbol. So we know that the number of the bottom is the atomic number of the element, which is unique to each element. Here that means the number of protons. So number of protons. And 235 is the mass number, which means the number of particles in the nucleus, which is the number of nucleons. Or we can also write it as the number of neutrons plus protons. Uranium 235 is a fuel used in nuclear reactions. Say the process by which energy is released from uranium 235 in a nuclear reactor. We know that this is nuclear fission because that's the thing that scientists are trying to replicate on Earth from the sun, which is nuclear fusion, but they haven't been able to achieve that. Hence, all we can do on Earth is nuclear fission by trying to basically split heavy nuclei like uranium 235 into two, and then the mass loss is converted into energy. A nuclide equation for this process is given below. Describe the mass and energy changes that take place during this process in a nuclear reactor. So this is what I was just talking about. So you know that the mass here given is 235 of uranium. Let's ignore the neutrons for now. And the mass of the products is 140 and 94, which is 234. So that one loss of mass when we convert uranium into xenon and seronium, I believe that's not important here. So this loss of mass, which happens when we hit a neutron to a heavy atom and it destabilizes. So yeah, this loss of mass in the form of neutrons is basically converted into thermal energy by nuclear fission, which is then released into the environment. So we can write this as the loss of mass in this reaction is converted to thermal energy, which is released. And just to find out the quantity of the energy, it's the mass loss into the speed of light squared, which gives the famous equation E is equal to mc squared. Describe how thermal energy from nuclear reactions is used to generate electricity in a power station. So these nuclear reactions, as we just discussed, produce a lot of thermal energy. What is this? How is this used to produce electricity? So the thermal energy released basically boils water. So the energy is used. There's a boiling water. A boiler is kept on top of it. So it boils the water to form steam. Now this high pressure steam turns the turns a turbine, turns the wheels of a turbine. So as the turbine turns, it's obviously connected to a generator. So by the process of electromagnetic induction, the generator produces electricity because it's a coil in a moving magnetic field. So that's why the thermal energy boils water, forms steam. The high pressure steam turns the turbine, produces electricity through a generator. State one advantage and one disadvantage of using nuclear fuels in power stations instead of using fossil fuels. So one advantage is that we need much less of a quantity of nuclear fuel than we need for fossil fuels to produce the same amount of energy. We say that the fuel density is much higher for fossil fuels. So we can say less quantity required. The disadvantage compared to fossil fuels is that a lot of toxic radioactive waste can get spread around an area, and the chance of accidents, the risk of an explosion or a radioactive leak is very very high, as we've seen in incidents like Chernobyl. Question 9. The table gives us information about three planets in the solar system. State the name of planet X. So you can see that planet X is just slightly lighter than the Earth, slightly closer to the sun than the Earth, and a slightly less orbital period. So this is the planet, just before Earth in the order of the eight planets in our solar system, which is Venus. It's Mercury, Venus, Earth. So yeah, Mercury has a much lower average distance of about 60. Describe a relationship shown in the table between the mass of a planet and the gravitational field strength of the planet at its surface. So we can see that the mass of, now we know Venus is the lowest, then comes Earth, then comes Jupiter. If you look at the gravitational field strength, the lowest is of Mercury, sorry, not Mercury, Venus, then Earth, then Jupiter. So you can see there's a direct relationship, so directly proportional. More the mass, greater the gravitational field strength. Yeah. Explain why distance from the sun is an average value. So this is a very interesting question. So as we know, we have the sun and all the planets in their respective orbits, orbit around the sun. But why is the distance not fixed? That's because this isn't your normal circle where the radius is constant. So the distance from the sun is fixed. These orbits are elliptical, as I've drawn this one. You can see that this part is closer to the sun than this part is. So this is how most of the orbits are. If this is the sun, most of the orbits are kind of like squashed circles, not perfect circles. So we can say that since the orbits are ellipses and not actually circles, we use an average value because the distance is not fixed. Part T tells us to show that the average orbital speed of the Earth is approximately 30 kilometers per second. So we know that speed is equal to distance by time. So here the distance traveled will be, the length of this or the circumference of the orbit, which while we mention it's an ellipse, the best way is to approximately take it as a circle. So distance is of course formula for circumference of a circle, which is 2 pi r. we have 2 into pi into average distance, which is the orbital radius, 149.6. So we're using average values, which makes it accurate. By the time taken is, of course, we have to convert the time taken into seconds. So, we have 365.25 days in which this orbit occurs. So yeah, it's basically, let me do this on my calculator, 365.25 seconds into, so we have 24 hours each day, 60 minutes each hour, and 60 seconds for each minute. So while it's a lengthy number, this basically comes out to 31.56 million seconds. So the orbital speed is going to be 2 into pi into 149.6 into 10 to the power 6 kilometers divided by 31.5 million. So, 3.15 into 10 to the power 1, 2, 3, 4, 5, 6, 7. So when we calculate this out, the average orbital speed comes out to 2 into pi into 149.6 into 10 to the power 6 divided by this value, which is 29. 29.78 kilometer per second, which is basically approximately 30 kilometers per second. Now, the last question is about the life cycle of stars. Protostars are formed first. So, protostars are formed when interstellar clouds of gas and dust, basically when they, heat up the cloud together, and, reactions within those clouds of gas cause thermal energy, and then they clump together to form a star. A protostar becomes a stable star when dash is balanced by dash. So that once a protostar forms and these clouds of gas and dust assemble together, there are reactions at the core which exert a radiation pressure outward, so the stars increase in size. But as they form a large mass, the gravitational pull of these stars also increases, which is inward. So if this is a star, it exerts radiation pressure outwards, but gravitational pressure inwards. So the it keeps growing, and it stops growing when the net force is zero, which is the radiation pressure and the gravitational force are equal. So we can write when the radiation pressure is balanced by the gravitational force. The initial fuel used to power nuclear reactions in stars is hydrogen, because we know this is what is nuclear fusion, which happens inside stars like the sun to produce energy, where hydrogen nuclei fuse to form helium nuclei and release energy. Stars that are approximately the same size as the sun, so small stars like the sun, become red giant stars, which then form a dash with a white dwarf at its center. So stars which are the same size as our sun, similar to that size, become red giants, and then when they use up all the energy stores, they form a planetary nebula after they cool down. Whereas, stars much bigger than our sun form red supergiants, then explode as a supernova, not a planetary nebula. So, yeah, this is question 10 complete, and that's the end of the paper.
Okay, that wraps up today's episode. We hope you found it helpful and feel more confident about tackling passovers. We've got plenty more episodes coming your way, so don't forget to subscribe and hit the notification bell to stay updated. Thanks for watching, and we'll see you in the next episode.